Welcome to the Crazy Hat Chemist. So today we're going to be doing the 17th video on nuclear chemistry, another half-life calculation. So let's get moving. Bam! So, half-life calculation number 2. The half-life of carbon-14 is 5,730 years. How much carbon-14 will remain after 6 half-lives in a sample that initially contains 25.0 grams? So, we're going to do this 3 different ways, and I'm going to show you all 3 different ways. You need to figure out which way works best for you, and maybe all of them work well for you, but each one could be a check of the other methods. So, here is one way, and I already showed you this way last time, and that is to use that knife that we have here, and we're going to divide our sample in half each and every single time. It's as simple as taking your calculator and your dividing button. Divide by 2, divide by 2, divide by 2. So we're going to start off with 25 gram sample that has the initial amount, and that is 0 half-lives. After 1 half-life, we're going to take that 25 grams and whoosh, divide it in half, and I got 12.5 grams. Well, I need to go all the way to 6 half-lives, correct? So I'm going to take that sample and divide it in whoosh, half again, and then divide it in half, whoosh, and then in half, whoosh, and then in half, whoosh, and then in half yet again, whoosh, for the final time. And you should see that that one right there at 6 half-lives is that is the exact number. Now, the numbers that I had have 3 significant figures, so I'm going to round this correctly to 3 significant figures, so this will be my final answer. At 6 half-lives, if you originally start off with 25.0 grams, you will end up with 0.391 grams of carbon-14 remaining after 6 half-lives. So that is one method. I'm going to show you a second method right now, so watch carefully. This one might be easier for you. I don't really know. The other one is just, the one that I just did is just chopping it in half with your knife each and every single time. Okay, so let's try another one. Okay, here's another equation. You might want to memorize this one. So there's a 1/2 to the power of the 1/2 is the number of half-lives times the original amount equals the amount that remains. So it's 1/2 to the power of the number of half-lives times the original amount equals the amount that remains. So the 1/2 is there all the time. That is like a constant. How many half-lives do we have in this problem? 6 half-lives. So it's going to be 6 to the power, it's going to be 1/2 to the power of 6 times the original amount. The original amount is 25 grams. And that will be, after doing that math, then I will get the amount remaining. So here's my setup. 1/2 to the power of 6, because it's 6 half-lives. 25.0 is the amount that was originally there. And we're solving for x, which is the amount remaining. So we're going to take 1/2 to the 6th power times 25, and then bam, there's my number. In fact, it's 0.391 grams. It's the same number of grams as on the previous work that we just divided it in half. Okay, hopefully that is the second method. That is another method that might work for you on all these problems here. Let's do the third method. So here's another alternate method to do. And remember, I used the half-life equation and the integrated first-order rate law. This is the one that is calculus-based that we're going to use here. So follow along carefully here on this one. There was some other information that was given in this problem that is absolutely necessary. Okay, the method that I'm showing you on this one particular slide right here will work with whole half-lives like the other 2 problems did. Now, this will work with non-whole half-lives as well. That's the key to this one, is that this problem right here, this set of 2 equations will work under any circumstance, and that is the beauty of this one. So let's get moving with this one. This is the half-life equation. T of 1/2, that's the half-life, is equal to natural log of 2 over K. Well, natural log of 2 is a number, 0.693. The half-life was given in this problem already for carbon-14, and that is 5,730 years. So I'm going to plug those values in there, and my unknown now is going to be the K. So I'm now going to rearrange this and solve for K. So I'm rearranging this, solving for K. So now I have natural log of 2 over 5,730. I'm going to do the division here, and this is what I get. So this is per year. Those are the units for this is per year. So it's the rate constant here is 1.20968 times 10 to the negative 4 per year. Okay, so that is one of the equations. Now the other equation is the integrated first order rate law. This is the equation that we need to use now. So we know the value of k, that's going to go in replace of k. Okay, now we're trying to solve for the amount remaining at a certain amount of half-lives. And so we already know the original amount. So we know x sub naught, which is the x sub 0. We know the original amount at time 0. That's the 25 grams, I believe it is. And then we know the amount of time. We know the half-life, which is 5,730 years, and we know the number of half-lives, which would be 6. So the total amount of time is the product of 5,730 times 6 half-lives. Okay, there's something else that we need to do here, and this is a rule of log. So natural log of a over b, that's a division problem, becomes a subtraction problem of natural log of a minus natural log of b. So we're going to take that integrated first order rate law and apply that mathematical rule to this. So this is what we get. Natural log of x sub t minus natural log of x sub naught is equal to negative kt. Now we're going to plug in the values. We don't know the concentration at time t, which is at 6 half-lives. So that's what we're going to solve for. But we do know the concentration originally. That was the 25 grams. We know the rate constant and we know the time. So we're going to plug those in here. So the natural log of time 0, that's x sub naught, is equal to 25 because it was 25 grams. We solve for the rate constant, that's the 1.20968 times 10 to the negative 4. That is the rate constant, that's equal to k. Remember, there's a minus sign, a negative sign right in front of that. Don't forget about that. The total amount of time here is 6 half-lives, and we know the half-life, so it's 6 times the half-life time, which is 5,730. So we're going to do a little multiplication here, and this is what we get, the natural log of 25, there's that, and then the product of the k and the amount of time. Okay, now we're going to bring numbers over to the other side, combine things, we're solving for x. That's all we're doing here is solving for x. So we're going to bring the 3.2 over to the other side. That's what we get. Now we're going to get rid of the natural log symbol. In order to get rid of the natural log symbol, we're going to take the opposite of that. So like the opposite of addition is subtraction. The opposite of multiplication is division. The opposite of natural log is the little e to the power of. So we're going to take that to the e. Okay, once we take that to the e, then this is the number that we're going to get. X sub t, that is the concentration at time t, that is the amount that remains after 6 half-lives, is 0.391 grams. Okay, that is a lot in that slide. This set of two equations that are in the yellow, that is the half-life equation in the yellow and the integrated first order rate law that's in the yellow, work every single time, even with non-whole number half-lives. If you are able to do that equation, you most certainly have graduated into another level of chemistry, and I'd highly recommend that. Check this really cool hat out. I made this myself. In fact, I wore this when I graduated with my master's degree. I got my biochemistry degree first, and then I got my master's degree, and of course, I'm wearing a graduated cylinder on the top. Isn't that beautiful? Hopefully that makes sense for you. Okay, that was the 17th video. I hope you have a great day. Subscribe to my channel, give me a thumbs up, and I'll see you next time. Bye now.